So to analyze your data, you first need to open the Excel file which you downloaded from the survey guide. So in my case, it's this one. So I'll open this. And the first thing you need to do, very important, is to rename the variable, to rename the measurement items here. So for example, here I have these measurement items for a product, so I'll name them A1, A2, everything. And then I'll shade them yellow, just so I can recognize them easily. So you do the same for all of these. And then for the demographics, you might also want to rename them to much more names. And then after you do that, the first thing you need to check for missing values or missing data in your data set. So I'll create a new variable here. So find the missing values. Count blank. Then you select the range across which you want to count the blank value. So in my case, this is the range. And now put a close bracket and press enter. So if it shows 0, it means on that data entry there is a missing value. So you just put it down. And because in some cases the data entries might be out, so you might have to rearrange the data so that you can track the missing values much better. Yes. So you can here sort, just expand the selection and then sort by missing values. Okay. And then smallest largest. I'll choose largest or smallest because if it shows me a larger number, that means there are some missing values. Okay. So in my case, even after sorting it, there are no missing values. So if there are any missing values, you have to delete them. If there's any missing value on the demographics, just take the out. If there are missing values here, if it's maybe only one, you can put the mean score of the two measured items and then put it there. Also, as if the missing values here, I would have calculated the mean value of SA1 and SA2 and then put that mean score here where there's a missing value. But if the number of missing values is more than 5% of your data on that particular entry, then you might have to delete that entry completely. So for example, on the second entry, if maybe I have let's say four missing values, and those four missing values are making up 5% or more of the total number of items that I have here, then I would have to delete this entry altogether because it's not right to put the main scores for missing values which are more than 5% of the total data. And then after you compute the missing values, you also need to compute the uninformed response. So some people that you want to answer to the question, rating 2 or rating 3 for questions, so you need to take those out. So I'll create a new variable here. And then the formula that we use is the standard deviation formula. So here it is, standard deviation. Oh, sorry. So standard deviation. Yeah. For this one, the focus is only on this measurement items. So you will select all ones here. And if I find a deviation of 0, it means all the numbers are the same. There is no difference, or there is no deviation from the mean for that response. So if there is a standard deviation of 0, we delete that because it's an informed data entry from an informed respondent. So to easily track that, you might as well just sort the data like we did with the missing values. So in this case, I'll sort it on uninformed and then sort from largest to smallest, smallest to largest. So here you can see that the smallest value is 0.9. So there are no missing values. If any of these was zero, it was going to be kicked out because that's an uninformed misconduct. Okay, so those are the preliminary checks that we conduct on the data. And then we move on to check the margin. So I'm going to open my SPSS. Okay, here, and then I'll open my data set. Okay, so um, right. So here we are. So I'll open that. And so here, yeah, we read the first row of the data, check that, tick that, and the rest are very important, so ignore them. So here we have our data. Before we check probability, we first need to compute these scores for all variables because I don't need these anymore, so I'll remove clear those. So to do that, I come to transform compute variable. And here target variable, I'll put the name of the variable that I want, that the name that I want the new variable to have. So the one that I want to compute right now is the name of AP, the name of college. So I will return AP, right? And then the numeric expression will be outcome statistical and choose a mean. And then I will select AP1. Make sure there's a comma between any two items and there's an open bracket after mean. So AP1, AP2, AP3, and the close bracket. So here we are, we have the mean for AP. And then I'm going to compute the second one, which is CA. So for that, we have CA1, CA2, and CA3. Okay, and then I'll move on to the third one, which is under ANG. And ANG2, ANG3. And then I will compute the mean score for the introduction. So close brackets. And then which is SA. So MS is for and finally revenge intention. I so I I4 and our mean scores. We use these scores to check for the normality and the outliers in the data. So to check for the normality, I will come to analyze, descriptive studies, and explore. So two options. I can select all of these at the same time, but for me, I'll just select them. Uh, I can either select them at the same time or I can select them. I can analyze them one by one. I prefer to analyze one by one. So I'm going to choose apology first, AP, and I don't need this. So I'll choose outliers. And for the plots, I'll choose and here normality tests. Normality close with tests. Continue. Okay. So you go. Now, here, what we want is for this value to be more than 0.05. So in this case, it's more than 0.05. Of course, here is less than 0.05, but it doesn't matter. So if the KS, the significance of the KS test is greater than 0.05, it means that the data for this construct is normally distributed. So you can see from the history here that it looks kind of like, so it's a little bit normally distributed. And then we check the box plots to see any outliers. So there are no numbers outside box plots. So we don't have any outliers. Okay. So we're done. And then we move to the next one. Descriptives explore. So I will now bring CA. I don't have to select the options again because I already did. So for CA, the data is not normally distributed because the normality tests are significant here. PLS and SW, both of them are less than 0.001. It's a very high significance. So the data is not normally distributed. It is skewed to one side. So we can see here it's kind of skewed right. Here it looks like a bell here, another bell, another bell. So we check the box. We don't have any outliers. We move to the CA and okay, let's see. Here, this is also not normally distributed. Oh, skewed to the right. And we have 1, 2, 3, 4 outliers, 2, 69, 14, 13, and 45. So we need, oh, got quite a lot of this stuff. So we need to remove this. All right. So we have 2, 69, 13, and 14, and then 22, 33, and 45. So we need to remove these at the same time because if you remove them separately, they change their identities. So we need to select them using the control function and kick them out at the same time. All right. So here we go. We have 2, and then we also have 14, and we also have 22, and we also have 33, and we also have 45, and we also have 69. Right for any. And that was much okay. Let's clear those. So after clearing those, we run it again. Let's explore. Okay. Let's see what we've got here. We still have more outliers. We need to delete these. So we've got 22. We've got 13. We've got 32. And we've got 44. And we've got 68. There we go. We clear this and run it again. It's cost 2 outliers, 15, 19. Let's keep those out. 15, 19. Clear. So analyze, explore. Okay, let's see what we've got. Whoa, some 22, 28, 32, 62. 22, 28, 32, 66. Let's see, just to be sure. 32, 28, 23, 28, 32, 60. 32, 22, 28, 32, all right. Clear. Again. Explore. Okay. We've got one more outlier. Yeah, after running 51, so we need to keep 51 clear. Explore. Okay. Now it's clear, right? So there are no outliers on it. We move on to the next one. Victims, explore. BA. Okay, let's see. We've got 1, 3. Okay. Try again. So it's clear now. Move on to the next one. SA. Let's see what SA has for us. 10 is not out of that. So keep this out. Run it again. Go. We've got no outliers. Right. Next. Explore. This the RI. Okay. Okay. No outliers. Now, usually what happens sometimes is when you clear the data from one variable, like we did with anger, it happens that you clear the outliers there, and then it causes outliers in some of the data that you already analyzed. It might cause new outliers to appear here. But for me personally, I just keep moving on. So if you want, you can just rerun them all together again to see if there are any new outliers coming up in the data. So try that for instance. Let's see. Here we go. AB, no outliers. CA, no outliers. Anger, no outliers. BA, no outliers. SA, no outliers. And RI, no outliers. The data is clean. And if you run it together like that, you will have the table for the numbers here. So you can see from just like we found apology is the only normally distributed variable, the only variable that has normally distributed data. So because most of our data is not normally distributed, we use PLS. Otherwise, I would prefer to use ARMS to analyze the data. So we are done with that. We move on to the next step. So the next step is the next step is to examine the common method bias. Now, we examine the common method bias using a technique known as Harman's one-factor test. Okay. So anyway, before I forget to explain these results, you will say that analysis indicated that the data for this variable was normally distributed. The rest of the variables had data that was not normally distributed. So that might be justification for the software that we use to analyze the data. And then you can use the box plots to explain that there were no outliers in the data because you don't have any entries here like a box plot. Okay, now we move on to uh, the common method bias test. So we use the Harmonious one-factor test to examine common method bias or common method variance. Okay, so you've come to analyze and dimension reduction and factor. What you do is you select all the measurement items in your model. So I select all of this. I will not use BA in my model, so I'm not select those. I actually should not have done anything about BA in the normality test. I remember deleting one entry out of BA, but it's fine. Never mind. Okay, after you select those, you come to extract. And here we are interested in the fixed number of factors to extract. Now, to decide the number of factors that you have extracted, you need to check the model that you have in research. So for instance, in my case, this is my research framework. I have 1, 2, 3, 4, 5 variables. So that means I need to extract 5 factors. If you have 6 in a model, you have to extract 6. So I extract 5 and go to this table, total variance explained. Now, what we want here is for the number on component number 1, the percentage variance explained by the first factor is less than 50%. So here we have 30%. So we're good to go. So here is fine. We'll move on to the next stage. Okay, if you were using Amos to run your to test for your hypothesis, you can also use the common factor method in Amos, but I imagine you might use PLS, so you don't have to use that technique. So here we are good. Let's turn out common method data. We'll move to the next step. So we move to the next step. The next step is the multicollinearity test. How to do that? I'll PLS. Right. So SmartPLS. Okay. Now, to be able to use this data in PLS, I need to save it as CSV file. So I'm going to save it as CSV file. I'll save it using today's date, 18th June. And save it as a CSV file and save. Okay. I'm done with this section. That I think was right. Okay. Now here we go. I'll create a new project. I will name this 18 June. Okay. Okay. And I'm going to import the data file that I intend to use. So I'll go to the folder I see the data file. Research methods. Here we are. Okay. Okay. So it shows it's green here, so the data is okay. All right. So I will draw my model. So in my case, the independent variables are CA, theory, potential ownership, and stability attribution. I will just control and I'm going to rename this stability attribution. And I'm going to bring my mediator, which is customer number. Let's take here. So align indicators at the top, and I'm going to right here. Outcome variable is revenge integer. Here we go. So more specific. Find the right. Okay. In my moderator. Apology. Okay. So here in this framework, what we are examining is whether, so we're basically examining the evidence of revenge intentions of customers towards telecommunications companies due to service failures. So if customers believe that the hypothetical reasoning here is that if customers believe that the service company could have controlled the service failure or could have done something to avert the occurrence of the service failure. And if customers believe that this failure will occur again in the future, they will be very angry towards the company. And if they're angry towards the company, they will want revenge against the company in some way. But if the company apologizes to the customers, then the revenge intention will be reduced. Customers will probably not want to revenge against the company because it has said sorry to them. Okay, so because here what we want to do is to test for what we want to do here is to test for multicollinearity. We bring in a new variable into the framework. So in my case, I have BA as a new variable. It's just a random variable that we want to use to test for the normality. So I'll set my indicators to the bottom and I will connect all of these to the random variable that I bring in. There we go. And then we calculate PLS algorithm. Okay, now what we want to check is the collinearity statistics, VIF. Click here, and we check the inner VIF values. And we want all of this to be green, or to less 3.3, or 5 if we are doing it all liberal. So here we don't have any multicollinearity problems, so we're good to go. So we close that. If any value here is more than 5, you probably have a multicollinearity problem and you need to report that, or you need to try and control that. But that's a different story. That's a story for another day how we do that. Here we don't have a multicollinearity problem. One. So you report this, you just take screenshot, or you can create your own table in the report. Like in my case, what I did was create a table like this. So these are the VIF values against the variable. So I just put them brought in here. No matter data. Okay. So no multicollinearity, and because we are good, after you take a screenshot, kick out this unwanted variable. We don't need you anymore, buddy. Go. So this is our model. So after testing for multicollinearity, the next we need to do is to test for discriminant validity. So basically, when testing for discriminant validity, what we want is to make sure that the variables that we have in our study are different. They are not the same. They are the same variable quoted in different names. So we want to confirm the differences among these variables. Okay. So to do that, we are going to connect the variables like this. And then we are going to calculus and then PLS algorithm. Okay. And for the discriminant validity, we come here, discriminant validity. Now, the numbers that we have here, these are the square roots of the average variance extracted. And here, well, perhaps before we go to discriminant validity, we will first examine the reliability. Okay, so I will come to reliability, construct reliability and validity. Now, for the reliability, what we want is for all of these numbers to help us to be greater than 0.7. So in my case, my reliability is very low. God knows why. Now, so I have problems with my identity. Okay. And then also check my loadings to check the convergent validity. So I'll open outer loadings and see. Now we want all of these to be more than 0.5 at least. At best, more than 0.7. That's the best case scenario. So that's why I have this 0.5, this one highlighted in there. Because we have some that are way lower than 0.5, we'll delete this. I'm going to come to my new model. Here we are. And those that are less than 0.5, we keep them out. Okay, so we select these three and delete this. If we run again, our reliability and loading should improve. So we check the reliability once more. Here we are. There's an improvement, but we still have a problem. Okay, so if you want to report the results as they are, you can just say reliability problems with current attribution, but the rest were okay. But there's another technique that we use to control for situations like this. We delete for data on the on the constructs that are causing problems with reliability. And to do that, you have this the reliability testing with SPSS. But I suppose you might not have that problem, so I will not waste time to do that in SPSS. Okay, so we have reliability problems, obviously. And for the loadings, there's an improvement. They look good, all of them. And if we check the discriminant validity, now what we want here is for numbers below the diagonal, the numbers below this topmost diagonal be less than the number on the diagonal. So we are good. All numbers are less than the square root of the average variance expected, which is on the diagonal. So the topmost diagonal. So we've got some discriminant validity here. And then check the HT ratios. What we want is for these ratios to be less than 0.9. So here we are good. We're okay. Right. So we're good. And then what else is there? Check discriminant validity, reliability, and validity. We'll check that. Oh, very important. The composite reliability. We want these numbers to be greater than 0.7. So here, greater than 0.7. So we're good. And the ADE, we want these numbers to be greater than 0.5. So we are good. And for some more conservative needs, there is a way of calculating another very important indicator of discriminant validity known as squared multiplication. The PLS doesn't do that for you, you have to do it by yourself. So I'm going to open this browser, search this term, CRFESMC online calculator. Okay, and open this first link. Statistical mind. Well, if you want, you can use it. Okay, I will use this. Go ahead and calculate. Now, what we do is we add the item loadings for all the constructs that we got for each construct one by one. So here we use the loadings. So I'm going to click outer loadings and I open this side. So for anger, I have two. I'm going to enter the loadings for anger 0.745 and 0.819. Now, what we want is for the SMC item R squared to be greater than 0.2. So we're good. And you see here the composite 0.76, which is precisely what we get here, 0.7. So you can do that for all of them. So each item will have each SMC. So there will be an SMC, an SMC, and so on. All of them should be higher than 0.2 if the loadings are higher than 0.5. So that's how we go about calculating the SAC. All right. Now, here we're pretty much done examining the measurement model. I guess we can now move on to examine the predictive model for the test of the hypothesis. Now, to do that, I will add my moderating effects here. So in my study, my argument is apology moderates the relationship between anger and revenge intention. So moderating effects. Right click, add moderating effect. The moderator is anger, and the independent variable is no. The moderator is apology, and the independent variable is anger. Okay, so I can rename this variable to say it's apology, anger. Okay, and I know that if I use this data, I will not get the results that I want. So I'm going to import just for the sake of explanation. Right, import the file. I am going to use this. Right, so there we go. There we go. Okay, sample size 72. That's what I want. But you have to use the data that you've been using all along. Okay, I'm just using this file just for the explanation. Okay, so the test for the moderating effects, test for all our hypotheses use the bootstrapping technique. So, but before we actually the model, we need to check three very important things. We have the f squared values, and then we have the r squared values, and we have the q squared values. So when you do the bootstrapping, sometimes it will give you the r squared values here, but usually it shows using the PLS algorithm. So if I add my moderating effect after I do that, I'll do the thing, and then I'll go here to check the r squared values. Now we want these r squared values to be greater than 0.1. So here they are good. So if they're greater than 0.1, we are good. It means our predictions are quite relevant. Okay. So for the r squared values, we are good to go. So this is a small predictive value. This is quite moderate. So our predictive relevance here is small to moderate if we take the r squared value into account. And then we also need to calculate the q squared values. Now, the bootstrapping technique doesn't show you the q squared values. You have to do that by blindfolding. Okay, so you just leave it there. Start calculation. And here we are. We want to check what we want to do these q squared values here. We want these to be greater than 0. So they are only for the dependent variables. Okay, anger and revenge intention which we have here. Anger, revenge intention. So the q squared values are more than it. So what that tells us is that the predictive relevance of the model is acceptable. And then because we are good to go, you can screenshot this added into your project. And then because we are good to go, we can finally do the bootstrapping. So I like to use 5,000 samples. I don't have any groups, so it's just a simple bootstrapping procedure here. Drink your coffee as you wait for it to complete. It's done. Okay, so we open the bootstrapping output. The first thing we want to check is the path coefficients for the direct effects. So in my model, what I had was CA and SA predicting anger positively, and anger predicting revenge intention positively. So if I check here, CA predicts anger positively, 0.3, and the p-value is 0.029. It's less than 0.05, so that's significant. SA, same thing, 0.041. There's a positive relationship between this and anger. And anger to revenge intention, there's a positive relationship, 0.261. Okay. So well, before we check those results, we also need to check the F squared values. Those are shown through the algorithm output. I'll just run it quickly and check the squares. Here we are. So we only check the F squares for the independent, for the predictor variables. We have SA, CA, and then we've got anger and apology. We don't check the F squared values for the moderating effects. We don't even have to check the F squared value for the moderate if we don't hypothesize any direct relationship between each and this one. So here we only have a moderating effect, not a direct relationship. So no need to check that. So what the F squared values tell us are the effect sizes. So the higher the F squared value, the higher the effect sizes. It's between 0 and 1. So we want these to be, the closer they are to 1, the higher the predictive the effect sizes. So here we have quite small effect sizes, so not a problem in this case. Okay, so check this to see the direct relationships between the variables. So these have positive relationships, as you can see. The beta coefficient, I like to use the sample means, okay, but because the professor prefers this, so it depends. So here there are positive relationships because the coefficients are positive. So the direct effects here are supported. Now we check the moderating effect here, anger by apology. The coefficient is negative and it's significant. What this is telling us is that if there's a negative here, it means the relationship between anger and revenge intention becomes less strong, or it becomes weaker if a firm offers an apology. So if a customer is angry because of a service failure, they will not be willing, or they will be less likely to revenge on the firm if the firm offers them an apology. Okay? So there's a moderating effect here, negative. If it was positive, the interpretation would be if a customer is angry, okay, and the firm offers them an apology, then they will be even more willing to revenge towards the firm, which is quite illogical. So this result that we have here makes more sense. Right. Now, the next thing after checking for the moderating effects is we need to check at which levels of anger this effect is significant, at which levels of apology, right, at which level of the moderator this effect is significant. So what we do is we check that using the algorithm output. We come to the simple slope analysis. We want this graph. Okay, so I'm just going to copy this to clipboard. I'll copy it like this. Right. And I'll open the Microsoft Word. Illustration. And I will paste the graph here. Okay. Okay, now here the green one shows apology at minus. This one shows apology at -1 ST, so low apology. This one is apology at B, and this one is apology at +1 ST. So that's kind of like high apology. So the result that we have shows that customers will be less willing to revenge if the apology is low and moderate compared to when it's high. Because here you can see the slope is quite, it's not, the slope is not steep. So they will only accept their apologies at lower levels. So if the apology is low and moderate, customers are willing to accept that. Why? It might be possibly because a high apology will be due to a very high service failure. So customers are less willing to forgive very serious service failures. So you offer them small apologies for those service failures. Customers will be like, oh, it wasn't that serious anyway. So that might be the interpretation. But well, I expect the apology, the slope to be more pronounced at a high level, but we have the opposite situations. We've got to find an explanation anyway, and that might be one of those. Okay, so that's the moderation plot. This is really very important. And then we come to back to the bootstrapping out to check for the mediating effects. So for us, our hypothesis was that anger mediates the relationship between this and this. And it also mediates the relationship between this and this. Okay. Now, how do we check the output for the mediating effect? We come to the specific indirect effects, and the output shows that we don't have any mediating effect based on the p-values. We want to check the confidence intervals as well. So we check the bias corrected confidence intervals. So here we are. We want, so this is a lower level confidence interval, and this is the upper level confidence interval. We don't want one of these to be negative and one of them to be positive. It's either both of them are negative or both of them are positive. That we have mediating effects. So here, this one is negative, this is positive, so we don't have a mediating effect. And this one negative, this is positive, we don't have a mediating effect. So these results corroborated by the p-values which are higher than 0.05. So we don't have any mediating effect. And the same might actually be used to interpret the moderating effect as well. You see the confidence interval for the moderating effect has 0 in between. Oh, no, no, no. Both of them are negative. There's no 0 in between because it's statistically significant. This is what both of them should be negative. We will check the confidence intervals bias corrected. We will check these on the bias corrected. So, what these results tell us, the indirect effects results, is that controllability attribution does not affect revenge intention through anger. Stability attribution does not affect revenge intention through anger. If these effects were significant, then we could have been saying something different here, like controllability attribution affects revenge intention through anger, but it's not the case here. So it is what it is. So that's about it. It's about it. And if the moderating effects are not significant, we don't really care to cause the moderation plot. Okay. The moderation effect might be significant at only one of these if it's not statistically significant in general. But if we find that it's not significant here, the moderating effect, don't dare to open the slope analysis. It really doesn't matter. Well, but if you want, you can. But it doesn't matter that much. Okay, so that's pretty much about the analysis. Okay.